Oh yeah.
So yeah, forgot. But anyway, so this is any such set. So with any coefficients p tau is a shift-invariant subspace of dimension s. We still have the same observation model as before. Now we have some mild assumption that, n is bigger than s, essentially. Still the same noise model. Now, what is our question? How well can we estimate x star in the minimax sense as before without knowing the subspace? Now, what does it mean without knowing the subspace, right? Well, we will go to that, but first, why is it hard? The short answer, it's hard because in particular it includes as a subproblem all sparse super resolution, essentially, where instead of resolving the frequencies, resolving the spikes or resolving the spectral measure of the signal, you just want to get rid of the noise. And this is actually a harder problem because what we know, if we, anybody who heard about super resolution probably heard that it works with the right rates, with what they call fast rates, and which are actually optimal, the right rates. When the frequencies, the spectral measure is well separated. It's basically then we have this incoherency conditions, and they know how to imitate lasso estimator and so on and so forth. But we really don't want to impose it. Ideally, we would like to be adaptive over the whole family of all possible shift-invariant subspaces of dimensions. So, okay, so we can, I guess, skip the rest of the slide. Essentially, what this is saying is that there are equivalent characterizations of shift-invariant subspaces of dimension S. One way of saying it is that X, the sequence, is an arbitrary exponential polynomial of total degree S. In particular, these are harmonic oscillations. This is the case where the characteristic number, your characteristic roots of your equation are on the unit circle, and are different. But then it's much more general. Essentially, any roots would work. Any and S numbers on the complex plane would work. So she had to leave for the day. Do you want to go ahead and do the someone can try to mute themselves. I think Ramina. Yeah, thank you. So, by the way, just before we move further, okay, so I write these things discrete, and I have this linear recurrence relations, and some people might, haven't heard about it that much. Oh, let me tell you something. If you had an ODE class and you had linear ODEs, so what I call ODEs, homogeneous linear ODEs, okay, then you also saw exponential polynomials. So let me tell you something. Discretizations with regular step of arbitrary solutions of ODE of order S, of ODEs of order S, give you this set. All possible. So this is simply discrete shadow, a minimal discrete kind of counterpart of the, of ODEs 101, okay, of ordinary differential equations with, S derivatives, linear ones with homogeneous left-hand side. And the punchline, the most important point here is that that equation is unpause. It's not such a big that it's linear. Okay, the problem is highly non-trivial because the equation is unknown. When you have like a manifold of linear things, you have a very non-linear thing as a result. Anyway, now, okay, so I will skip this slide. This is basically what I said before. So if you define, let me just define delta as a shift operator. So delta is a discrete forward shift. It shifts the whole sequence by one. Forward or backward, it doesn't matter for you in this talk, in one direction. And then it's clear that you can write these equations, linear equations, in the following form, that polynomial of delta applied to your sequence. So there's this linear operator, which is, there's some, if you just read this and read that, then you get this, right? So polynomial of delta applied to X is 0. So in other words, any subspace is just the kernel of such linear operator, where P of delta is the polynomial with P tau its coefficients. Nice. And now the theory of such ODE, or such, they call this ordinary difference equations, or linear recurrence relations, homogeneous linear recurrence relations. It just parallels continuous ODEs. So essentially from any ODE with some capital, polynomial capital P applied to the derivative operator of F, Okay, this solution set, if you discretize it by 1, will recover you these solutions here. It's really, in some sense, it's even not less general, because there are, I mean, in certain sense, you can also go in the reverse direction, but this is beyond the scale of this talk totally. Now, and such equation we can describe, instead of describing it in terms of the coefficients of P, we can describe it in terms of the roots of P. That's very natural, right? That's what they do in ODE class. I mean, this small p is called characteristic polynomial of our difference equation. Same as capital P is the characteristic polynomial of the continuous ODE. And then we can talk about small p in terms of the roots. Now, natural way of talking about it is essentially comparing, looking at their radius. So things in terms of the stripes, vertical stripes, and I want to explain familiar from ODEs, they now correspond to circles, being outside or inside the circle. In particular, if your roots, call them z1 through zs, of the characteristic polynomial of degree s, if they are inside the unit circle, then you have stability. That means for any initial conditions, bounded initial conditions, your output remains bounded. In fact, if they are strictly less than 1, it actually goes to infinity, to 0. So you have what is called asymptotic stability. Now, finally, another geometric perspective is that I'll just briefly remind that, well, these shift-invariance of spaces that I mentioned, right? They are simply solution sets of the corresponding difference equations, or in other words, kernels on CZ of this P of delta operator. Great. And in fact, there is a really fun exercise for anybody who ever wondered, do you need, like, why do you need this, like, in linear algebra, what is it called? Frobenius Jordan theorem, right, with cells. So why this thing with cells, why is ever needed? This is one example where it's needed. In fact, using this theorem, you can show that it's one-to-one. In fact, any shift-invariance space of dimension S it must be a solution set of such an equation for some P, and in fact, unique equation. Anyway, okay, so consider this the boot camp. Now we can talk. Our set over which we want to characterize the minimax risk, statistical risk, is this squiggly XS. Okay, it's the union of all S-dimensional shift-invariant subspaces of CZ. That's our goal. Now, minimax risk. So to be proper, to talk about actual statistics and not something in our head, we want to, define what is the optimality, what is the performance criterion. And so what we do is the following. So we consider this rescaled norm, which is just the empirical norm, so rescaling by the observation domain. This is, the squared n, 2 norm is just this. So the squared, the rescaled L2 norm of, of a sequence on this central domain, minus n to n. All right, so then MSE just writes like this in this compact form. Then if we fix some confidence level, so we want to do some, kind of PAC type bounds, so epsilon delta stuff. So what we want to do is we fix delta, that is the confidence, and then we can define worst case delta risk for an estimator over any possible, any given set capital X, which is simply this: it's the minimal width of the confidence interval, right, for this delta. So in other words, it's epsilon such that with probability at least 1 minus delta, I'm at most epsilon in terms of this MSE, right? And so the point is that it's uniform over X star, right? So then minimax delta risk, I call it like this, is just so if this risk n delta is the maximum risk over my, set, whatever the set is, capital X, for a given estimation procedure X hat, so a given estimator, right? So now if I take infimum overall measurable functions from Y, I get what is called the minimax risk. Risk with star, risk star and delta of my set. That now doesn't depend on the estimator because I took a best estimator. And then Nemirovsky's question is this: what is risk n delta star of the set xs? Now, let's see what we know about it. So what classes of Shift-Invariance of spaces there are interesting classes? Yeah, of course, I can talk about polynomials and sines, but in this slide, I kind of want to start with basically with sinusoids. So let me consider the following construction. Let T be the unit circle. So T is just a complex unit circle, not the disk. And then I discretize T. So Tn is the set of the roots of unity of degree to n plus 1. In other words, Tn are the basic, their phases are the basic frequencies of the discrete Fourier transform with this bandwidth, corresponding to our observation horizon. And then I define the following set. This Tn angle S, what I do here is I take arbitrary, tuple of S, S points from Tn. So in other words, this is the grid setup. This is like vanilla sparse recovery, which corresponds just to sequence denoising, frequencies being on the discrete Fourier transform grid. Okay, grid completely, grid kind of abstraction of the sparse recovery. And then I have another set, a way, smarter set, which is TSN. Now instead of just selecting points in the nodes of the grid, I can now select any points from T, but the pairwise separation should be as it is, as if they were in the, separated by one beam of the discrete Fourier transform. So no closer than two nodes of the grid. So I kind of imitate the grid in terms of incoherency, but now I'm gridless. This is this TSN set, separated as tuples, in other words. And then let me define, for any given tuple, I can define the corresponding Shift-Invariance of space, which is simply, it corresponds to the equation with its characteristic roots. So in other words, with this polynomial P of z, that is that stuff. Okay. And then I can take a corresponding subclass of, subfamily of the family of all Shift-Invariance of spaces by taking my tuple to be in some set of, some subset of CS, of, CS. And then I have the following inclusions. Okay, so first of all, and below is what is the English characterization. Okay, but now in this formal language, the first line is just telling what we do. So this squiggly X. So when omega is the first set, the grid set, then you get signals with grid spectra. This kind of grid stupid sparse recovery. Then if you take instead, then from the larger set, TSM, you get separated line spectra. So signals with well-separated line spectra. Now, if I drop the separation, that's really the important transition here. If I drop the separation, I get arbitrary line spectra. So in other words, what it means line spectra, right? That means that my sequence is a linear combination of at most S complex cosines, complex exponentials with arbitrary frequencies of these exponentials, arbitrary. And then finally, our problem, Nemirovsky's problem corresponds to this set. So when omega is just CS itself. And so obviously I have these inclusions where something dramatic happens in you can argue that in all three places, but long story short, even in this slide, so what people did in kind of classical sparse recovery, a la Candes and Fernandez Grande 2014, or Reicht 2014, with students, so Tank, Bascar, Reicht. Essentially what they did is that, okay, from this stuff that is obvious, okay, this is one line for like PhD student, they managed to get here with the optimal rate. Okay, and then they said, okay, we kind of don't know what to do here. The way we do things doesn't work, and actually you can show that it doesn't work. It's not that they don't know how to do it, it actually doesn't work here, and we don't know how, if it can be done the other way. In fact, not many people realized, apart from Nemirovsky and Yuditsky, that it actually can be doable. that the lower bound doesn't apply. But anyway, so let's go. So let's just very quickly look at what is this grid spectra. I mean, okay, so something slightly technical starts. I do need to introduce discrete Fourier transform. And this is the discrete Fourier transform. So essentially, you define this he and k is just the sequence. It's basically it's the sinusoid with kth base frequency, the discrete Fourier transform. So this is with zk, which is k over 2n plus 1, like exponential, I'm sorry, exponential I 2pk over 2n plus 1. I'm sorry, this he and k, it's actually zk, so it's actually the root itself. Right, and so if now we want to take the corresponding complex exponential, we take this in the power minus t or t and increase t, right? And now this is just a Fourier coefficient with a proper normalization. This the kth discrete Fourier coefficient, right? And then saying that a signal x star, okay, in some shift-invariance of space, but now the shift-invariance of space, let's say with, frequencies on this discrete Fourier transform grid, saying that it's a sparse, it has a sparse DFT, right? It's the same as just saying this. So it's in the shift-invariance of space with this Z1 through ZS on a unit circle, but in the nodes of the grid, of the discrete Fourier transform grid. Right, and now we know that this is an isometry, this Fourier transformation like this, right? It's an isometry. This is what's the word? Self-adjoint matrix, right? Self-adjoint and I'm sorry, what's the word? Hilbert, basically complex analog of the orthogonal matrix, right? Unitary matrix, right? So now, because it's a unitary matrix, we just do Parseval and go to the Fourier domain. And magic, we just in the situation of Gaussian sequence model with a sparse signal. We just apply Fourier transform. The noise with the complex Gaussian distribution remained complex Gaussian distribution, right? Observations transformed in a way we know how they transformed. Because we use L2 norm as a performance measure, we have orthogonality, so nothing changed here as well, right? After taking Fourier transform. The only thing that changes is that the signal is now sparse. And we know what are the rates, the optimal rates now, right? So we know that for any selection of these roots, right, from the grid, in the nodes of the grid, the right rate is this. So I will mask from now on this part, sigma square over 2n plus 1 is kind of non-informative. It's always there. What is informative is the factor that multiplies it that depends on s and on n in some way. And this is the right dependence. Okay, s log n plus log of 1 over delta. All right, so, and in fact, this is already the lower bound. So we know that, interesting thing, right? If our final goal is to characterize minimax risk on x of c power s, but we actually know that even in denoising, if you in denoising do a simple, bias and lower bound, you already will see that even in denoising, you get this rate. So even in the grid denoising, right? So on the grid, you already get from all possible subspaces corresponding to these locations in the nodes of the grid, you already get s log n, plus confidence term log of 1 over delta. Well, that means that things can only get worse from this, right? I mean, because x of CS is a larger set. We just allow more possible tuples of characteristic numbers. On the other hand, we also know what is the best possible scenario is that if magically it will turn out that minimax risk, the upper bound for the whole squiggly x of omega is of maybe up to polylobes. Well, it turns out to be the case. Go and see something. But before the conclusion, I'll just elaborate more on the connection. Okay, so educated people working on this narrow area probably read this paper. I first one, but this because essentially there are two papers, and maybe there are others where people things with names like certificate or support memory in harmonic super resolution. Essentially, managed to show that this lower bound is not on the, so allowing the statistic roots to be only in the nodes of the grid. Now these are allowed to be anywhere in the circle under the separation where the Fourier transform. Well, just like be instructive why it doesn't work beyond separation assumption. Well, essentially, what they did last and they try success. What's the main idea of Lasso? Lasso tells you that Lasso with sparse denoising without any metrics in the and you quickly recover in the sparse. You just quickly recover the rates log n over n. And then Lasso says, well, wait, now I have a metric, so I do kind of regression. But if my with respect to the all possible, set of signals, not necessarily on the whole RD space, but like with respect to sparse signals in some sense, then I'm still good. Then essentially, if the matrix is well conditioned, then up to the condition matrix of this number of this matrix, I still have the same rate. And then for some reason, it's kind of it looks very nice. If the frequencies are separated, then the corresponding matrix in this problem, whatever it is, will actually be well conditioned. It turns out to be the case. It's precise threshold. What it means, like how well should it be conditioned and getting rid of some loss. It's actually a theoretic problem. It's related to what is Cyber measure.
What in Dmitrii?
Sorry? Oh, thank you. Thank you. Let me recap. Now, is it better? Okay.
Yes, thank you.
So, yeah, I need to change those. So essentially, this is what they do. Okay, so they said, okay, so if I'm on this set, so if my signal is a combination of a small number of complex exponentials with unknown frequencies, well, that means that if I kind of do infinite Fourier transform in a way, okay, that corresponds to spectral measures of all sequences. So I kind of think about all possible sequence that I can go in both ways outside of my observation domain. And in the Fourier terms, that corresponds to considering instead of the grid, the continuous, the circle on which I have a spectral measure now. And now I can try to say, okay, so what they call atomic soft thresholding, right, or atomic denoising. So essentially, I imitate Lasso, where instead of D, I have continuum dimension, but I still have S. So in other words, what they do is that they have this operator phi of nu, that is the sequence of moments of nu, but essentially phi of nu is the matrix, which has, in a way, I mean, like the rows of, it has 2n+1 rows, but it has continuum of columns, okay? And multiplying this matrix by a spectral measure corresponds to, to this operator, phi of nu. Essentially, it means take the sequence that you get, by considering a signal with this spectrum, with this new Fourier spectrum, but what you will get in the samples from -n to n. And then they say, okay, so I'll just do linear regression with respect to this parameter. And I have L1 norm regularization, which for measures becomes total variation regularization. I mean, that there is a whole theory of why it actually works, right? But this is the message. I mean, the underlying reason it works is because Lasso works under RIP type conditions, and RIP type conditions here are actually one-to-one related to separation of the frequencies. This last part is not obvious from what I'm saying, but think about it, there is some relation, right? If the spikes are really close, if the two spikes of the spectral measure, for example, are really close, then we know that aliasing, right, this Dirichlet kernel will make them blur together. So you lose identifiability even here. So you have no hope of recovering mu star that actually generates UX star. Well, here's the whole crux. Okay, so the whole punchline is that who said that you need to recover mu star? If you think about it for a second, it's only clear that if you can recover mu star, you can also recover the signal in the time domain. However, if you cannot, why it happens? It's because the spikes are very close. But if they are very close, they seem to produce the same signal. Yeah, that's kind of the main idea. In other words, you don't care for estimation where you need to do prediction. Okay, so doing plugin is not always a great idea, in other words. It's only a great idea when plugin solves you an easier statistical problem. If it solves you a harder statistical problem, then you're overkilling yourself. Anyway, now very quickly, okay, so to present the construction, I need the notion of a reproducing filter. Reproducing filter is just the discrete version of a reproducing kernel, if you will, but really, we don't need to remember even what reproducing kernels are, okay? So let me just define the following thing. Cm of z is the space in C of z, it's the subspace where you have zeros outside of the central M region. So it's kind of another way of considering subspaces of finite dimension in CZ, which is kind of very much not shift invariant. Okay, so when you shift, the whole thing changes here. In some sense, it's a dual object. But anyway, so what happens is that I will take filters, I will call filters sequences from this space, where M is the bandwidth of the filter. And so if I take such a phi of delta and apply it to a sequence X, then this is just linear time invariant convolution with this discrete kernel with coefficients given by phi tau. LTI filtering from signal processing, okay? That's some picture, never mind. Just to say that there are some edge effects, right? I mean, if to compute this thing from the domain from minus n to n, I kind of need to look at this kind of subdomain, otherwise things go out of the boundary. And no periodicity here assumed, so this is important. So anyway, so we call a filter reproducing on X on some set, a subset of CZ. If this holds, okay, you can formulate it in terms of polynomials that I minus, identity minus phi of delta divides the polynomial P, characteristic polynomial, but I won't need it. I just want to say that we call, if we are given some subset of the set of sequences, we call a filter reproducing if basically reproduces all sequences from this set. So phi of delta applied to X as a sequence gives you the same sequence, magic. Well, I mean, it's kind of clear from this definition. If you look at it for a couple minutes, you will see that, well, maximum reproducing set for any filter is actually a shift-invariant subspace. And in fact, any shift-invariant subspace of dimension S is in particular reproduced by P. Well, I wrote P, but actually by P minus 1. This is a mistake. So, but the point is that the next question now, for some statistical reasons, I want to have the following. So I'm looking at the subspace. Okay, this is the next slide, but just before, let me do the following remark. So why the notion of this reproducing filters on subspace? Well, because reproducing filters correspond to unbiased estimators. That's why. All right, so what I mean is the following. Instead of X, let me filter with this phi, whatever phi is, let me filter Y, where Y is X star plus the noise as before. And X star is from a subspace that is reproduced by this phi. Well, if I look at the expectation, like on the bias, in other words, I'm looking at the bias. This is linear, phi is non-random. What I get is just a reproduction error, which is 0, because it's a reproducing filter. The whole error is the variance, as you would expect for the reasonable estimator for a subspace. It should be parametric, no bias. Space is not compact, so no bias. And so what happens is that for a reproducing filter, the MSE of the corresponding estimator, this would be a corresponding linear estimator. Okay? What is this? This is a linear estimator, but because the subspace is shift invariant, we also want a linear estimator to be not just linear, but also in some sense shift invariant. Well, in this sense. Now, the point is that MSE of such an estimator is just controlled by the L2 norm of the filter, just by the same calculation, right? So cross term goes away and you get the variance, but now the variance turns out to be that. Now, the thing is that the reasonable question now is this, right? So now if we have a subspace of dimension S, but now our observation horizon is n larger than S. Well, linear estimators, they would be LTI filters with filters living in, Cm roughly. Cm where m is, let's say, half, n over 2, something like this, to account for age effects. And so the question now is how, the first question you might ask, just even for a given shift invariant subspace, not all of them at the same time, just, a given one, but arbitrary one, how fast the norm decreases with n. So in other words, if I look, let's say, at the minimal norm reproducing filter in terms of the L2 norm for a given subspace of dimension S, but now the filter is with bandwidth m larger than S. Well, I mean, this gives me a linear estimator, right? And its variance is sigma squared times the squared norm. So I would expect that if these estimators make sense at all, which they hopefully do, I expect this to decrease, squared norm to decrease as, S over M. Turns out to be the case. Indeed, in fact, what we lose is a factor of 2. And we don't have a proof, but it seems to be optimal. And not because of triangle inequality. That's the fun part. But because of something else. But another thing I want to know before I move forward, this, by the way, is an observation by Dmitrii that was made in my presence in real time. Another observation is that, well, I mean, by Parseval, L2 norm of the filter, of the sequence of coefficients of the filter, right, this phi, is the same as the L2 norm in the Fourier domain. And now, because of all these allusions to sparsity, it seems that I would want to look at norms in the Fourier domain in general. So, for L2, it's the same, but generally, other LP norms, they are better to be looked for the Fourier transform of the filter. And by the way, a small remark is that just from this, what we see is that such linear shift invariant, so LTI estimators for a given subspace actually recover you the standard vanilla parametric rate for shift invariant subspaces, up to, factor 2, just because of this result. This is a very simple result. I mean, it's actually ingenious, but in terms of technicality of the proof, it's very simple. It's like 3 lines. We call it projector trick because, in fact, the right filter phi is obtained in some way. You can look in one of the first pages of the paper. It's one of the 2 propositions referred to as earlier work. I think it's called projector trick. Well, essentially, this phi is obtained from a certain row of the projection matrix. You have to choose the right norm, the row with the right norm. Anyway, now, another trick I want to mention before stating the result to give some intuition is this. So what about other norms? So once again, we're kind of doing, hopefully, sparse recovery. So we would probably want to look at the L1 norm next. So what about an L1 norm in the Fourier domain? So let's say, so in other words, do I have a norm, a filter with L1 norm of the right order, which, because of the normalization, so with the right rescaling, if you believe me in the rescaling, the scaling in S is now S for the norm, not square root of S. Right? As if the filter was sparse in the Fourier domain, essentially. Right? Well, I mean, it turns out that yes, such a filter again exists. And what you would have to do to obtain it is that you take the previous L2 norm filter and square it, which means square the polynomial. So you, in terms of filters, you do autoconvolution. You consider convolution of straight phi with itself to get the squiggly phi. And then again, it's a simple calculation. This beat is due to Denoising. Now, actually, what happens is that this is not written here, but if you just combine these two facts and do a bunch of statistics on top of it, in certain way that we can discuss, but long story short is that intuitively that would already potentially give you some result because you have control on the L1 norm at the right rate. So L2 norm control, now adaptation to the unknown subspace. I mean, what is the important point is that both these facts hold for any shift-invariant subspace of dimension S, where filter depends on the subspace, but the right-hand side doesn't. I mean, this result is corollary and the previous result. The point is that in these inequalities, the right-hand side does not depend on the subspace, only on its dimension. And so we have now with L2 norm set of possible, search space, L2 geometry is usually not very good for adaptive estimation, as we know, right? I mean, L2 ball is too massive, it's too round. But now with L1 ball, we have a chance. And it turns out there is a way to exploit this chance, and this is the work done before, including my papers from whatever, 2016, 17, and so on. Like, I mean, I'm not saying it's easy, I'm just saying it's known for a long time. Now, the problem with this is you're losing. And why you're losing? Well, the thing is that the L2 norm actually appears in this construction, and the L2 norm of this mu filter, this squared filter, unfortunately, it's not of the right order. Because the only bound you have for the L2 norm is that it's smaller than L1 norm, because nobody told you that the filter is actually sparse. Okay, so the L2 norm is S over square root of M. And this is actually where you lose. You don't lose in the sparse example, because in the sparse, it's actually the same filter if you square it. The filter will be just once indicator of the spectral support. But here it is not, it's just some square. And so you have changes in the magnitudes of entries potentially. So, well, now let me announce the result. Oh, now I want you to believe the following. If we have control over three norms with the right scaling factors, in fact, this implies control. In fact, it's enough to take two norms here, L1 and L infinity, the two extremal norms. All the others you can interpolate. But the point is that you need to show the following, that if X, let me instead introduce this, because this we can actually show it. And so let me just start with the result instead of what we would like to have. We actually have it. So we have the following result. This is the core. This is the core result actually of the paper, and it's approximation theory rather than statistics. This corresponds to proposition, the key proposition in the paper. It's shown in page 9 and 10. And anyway, so let M be larger than S. I have any shift-invariant subspace X of dimension at most S. Then there is a reproducing filter depending on the subspace of length of 9M at most, so with this bandwidth, such that its norms in the Fourier domain, all LP norms, at the same time, that's crucial, at the same time, have the right orders. And these orders are, well, as you would expect, up to this rescaling, the right rescaling, and up to a constant. C star is a certain universal constant. Square root, well, I mean, square root of S for the L2 norm, but for any LP norm, it's S power 1 over P. Basically, as if Fourier transform were sparse. So for some reason, this is what you need in statistics. Okay, so if you go back to this hardly readable result, basically, Oracle inequality that you are able to show will be such that essentially all like these three norms will appear. The L2 norm term will appear as something adding up to the expectation. Okay, the L1 norm term will appear essentially as the stochastic term, but sorry, the model selection term. That's the proper equation for statisticians. So L1 norm kind of appears because of normal selection, model selection here, and this is where you get the log n. So S log n. So S log n comes because of the L1 norm being at most S. Then there is also S that sits there, which is the squared L2 norm, which means that squared L2 norm cannot be, you cannot afford it to be larger than, well, S log n maybe, but actually it's S. And then what some folks here might not know, actually I didn't know it before, is that to get the right deviations, where log of 1 over delta is not multiplied by S, but is just summed together. You actually need control of the L infinity norm, but this you have. So this term should be constant. So you see that L infinity should be constant, L1 should be S, and L2 should be square root of S. So this is what we need. So very quickly, okay, in a few minutes, I just want to go over the proof. Now, here's what I will do. I won't go over the proof of the statistical part, not because it's easy, but because it's written there and because it's less, it's a worse use of your time. You can read it and you have, kind of background for this. This, however, approximation theoretic stuff, I think it's more useful, like I didn't know it before. And this is kind of the core thing, that this is the punchline. This is how you get to optimal. So essentially, very high level picture is that we have two tricks that give us the right L2 norm and L1 norm separately. And then we need a third trick that resolves our problems, that kind of marries the two results together. And this is related to Lagrange interpolation, as it turns out. So I'll try my best to communicate this. So here's the intuition. I start with, I'm giving, producing, forget everything about adaptive estimation, all this noise. So we just are given arbitrary shift-invariance space of dimension S. It's a fixed one. We don't know which one, so whatever we do should work for any of those. But there is no noise, there is no randomness. We just have, linear algebra related to this type of subspace. And so what we know is that we have a filter phi of length m for m larger than S with the following properties. Phi has small L2 norm in the Fourier domain always. And phi understood as a polynomial with its coefficients phi tau. The square of this polynomial has small L1 norm. So if you take this convolution of that sequence, take the Fourier transform, now this thing has small L1 norm, but unfortunately can potentially be large in L2. Now the question is, what happens? Well, if I look at the square of the polynomial, and in the Fourier transform, what I do is that I look at the values of the resulting polynomial in a unit circle. Well, in the grid of the unit circle, in fact, right? In the roots of unity. So now, if I look at the L2 norm, and I'm saying, well, L2 norm of phi was small, but now L2 norm of phi squared suddenly is not, right? Why this could happen? Well, if you look about it, because it's the same grid as before, well, actually twice more, frequent grid, but that's details. So it's essentially the same grid as before. So the only reason it could happen is because phi was larger than 1 at some points in absolute value. When phi is larger than 1, this is if and only if phi squared is larger than phi. And the only way phi squared can be larger than phi is when phi is larger than 1. And so the problem potentially happens not because of the small values. Okay, there are many small values in the grid of phi, of the absolute value of phi. Right? I mean, they are not zeros because nothing is sparse here. But those that are smaller, they only will decrease after taking square. It's those that are larger than 1 potentially that cause the problem, where the support estimate actually lives, right? This dual certificate, they do it for another polynomial, but it's a similar principle. They look at the points where the value of the polynomial is larger than 1. So the right polynomial, it actually kind of scaled to 1. And so you compare its values with 1 and not with something else. So that's kind of the idea, is to correct this. So let's try to come up with a filter that looks like phi squared, doesn't have too much different L1 norm, but has adjusted L2 norm. And then hopefully, if this like adjustment mechanism is smart enough, we'll actually get all the right norms. There are only so many things you could do that make sense. And how would you do it? Well, I mean, basically, try to just correct the values that are larger than 1 at these where it happens with 1. Intuitively, that should not cause you too much problem in terms of reproducing the subspace, well, in terms of, approximation, essentially, because, I mean, what matters is not how large these values are, but what are the locations of the spectral support. And the maximum locations will still be the same. It'll just the maximum values will be 1 instead of something larger than 1. Long story short, it actually works. And the right way of formalizing this is as following. You do the following construction. Okay, so I define support on the grid. So support of a polynomial on the grid is this. It's just a set of grid nodes. So degrees of, roots of unity. I need a minute, I guess, just really a minute, and I'll be done with it. So you look at the roots of unity, so nodes of the grid, where the value of your polynomial, whatever the polynomial is, phi, absolute value is larger than 1. And this is a certain subset of the grid. And then I'll do the following. I'll try to find, so okay, first of all, here's my construction. Here's the filter that I'm actually using, my oracle, that has all the right norms. It will be phi squared plus correction. And correction is of this form. For some reason, we will understand in a second why this form. So rho star, where rho star is a certain other polynomial, times phi squared minus phi 4, square of the square. Where rho star is the following thing. I minimize over polynomials of degree m the maximum on the unit circle among polynomials that interpolate 1 over phi squared. So in English, I'll try to divide over phi squared. So rho star is the analog of, the proxy for 1 over phi squared. Like if you pretend for a second that rho star would be 1 over phi squared, right? Then what you would get, here you would get phi instead of phi squared, right? Because 1 over phi squared times phi squared minus phi 4, right? What is this? It's 1 minus phi squared. Phi squared goes away and I just get 1. Not even 1, right? But this is on the support. I interpolate on the support, right? And so on the support, this thing will be 1 now. On the support, instead of phi squared, I get 1. Right? On the other hand, elsewhere, outside, because of this criterion with rho, okay, if I know how to control these norms, which I actually do, it's a basic Fourier stuff, which I will omit now, but it's even in the slides, you can find it. The next slides, I will share the presentation. But basically, because of this taking minimal norm interpolator, I can, outside the support, I can control the error. And outside the support, I pretty much still have phi squared. And so L1 norm guarantee will be preserved because of this approximation stuff. At the same time now, L2 norm, and in fact, all the norms, if you look at this, because you take this criterion here, in fact, all LP norms, because of the support correction, will turn out to have the right order, S power 1 over P. I can tell you that I was really happy to come up with this trick. It was kind of 2 years ago when suddenly just came without any just like came by some twist of fate. I was thinking about something else. And then it turns out that the trick was, I think, known to approximation theorists. I mean, the general idea that how do you divide over a polynomial to get a polynomial? Well, I mean, the problem is 1 over polynomial is a rational function, is not a polynomial. Well, you would interpolate the values of 1 over your polynomial. So your Lagrange interpolation polynomial, where your interpolation is, either Lagrange, but now if you have to choose a polynomial, you put a criterion there. that is in your problem. And our problem is this like maximum on the unit circle. So because I'm taking maximum on the unit circle here, this rho t is the maximal norm of a polynomial on the unit circle, subnorm. Because of this, that allows actually to control all p norms starting from infinity. I mean, that's kind of the punchline. There is, pretty much a sketch of the proof there, but we are not going there. Like essentially, you need some stuff. I mean, that's really the key idea. After you kind of look at this, things will happen. Okay. Well, just very small remark before I finish is that that's really important. That's algebraic form. This correction, you can kind of potentially think about other correction ways. So kind of interpolating other polynomial, maybe something like this. Now, and then, instead of multiplying by phi squared minus phi 4, multiplying maybe some power series or something like that. Now, the thing is that this is what you need. That's the reason. I mean, I need the filter to also be reproducing on my subspace, right? Which means that 1 minus phi, which actually means that 1 minus phi star, whatever my phi star is, should contain 1 minus phi as a factor. Right? Because 1 minus phi will then zero out all the sequences from my subspace. Great. And that's the reason why phi squared was reproducing, because 1 minus phi squared is actually 1 minus phi times 1 plus phi. And so it divides 1 minus phi. And so it reproduces. But now it turns out that here, this guy also divides 1 minus phi. Oh, why is that? Well, because it divides 1 minus phi squared. And why is that? Well, 1 minus that business is what? It's 1 minus phi squared plus something times phi squared times 1 minus phi squared. And so 1 minus phi squared is there. And so this thing is also reproducing. That's it. Summary. This was the construction of the oracle that shows you that for any shift-invariant subspace, there is an oracle, which is a shift-invariant reproducing kernel, so shift-invariant LTI filter, okay, with LP norms of the Fourier transform of the right order, S power 1 over P, which allows you then statistically to adapt to solve this adaptation problem. I did not go into statistical mechanism, of adaptation. Essentially, there is not much novelty there with respect to what it was. There is a slightly different decompositions, but basically, it kind of was already clear from the previous work that if you have all the right three norms, at least it was clear for two norms, but the L infinity norm is not much different. So essentially, you need all three norms, and then you will have the right statistical rate. The question is, in this guy's approximation theoretical, show that for any shift-invariant subspace of dimension at most S, there is a filter that has all the three norms in the Fourier transform at once of the right order, as if, this kind of corresponds to the scaling corresponds to sparse recovery, where the filter is just sparse on the support, just ones and zeros, and so it has all LP norms of this. I just, S power 1 over P. I'm done, I think. Thank you very much, and I'm sorry for the longer, for going over time. We still have time for questions. I would be happy to answer those.
Yeah. Thank you so much, Dmitrii. So do you have any questions from the audience online? I didn't see, but I got a question. So Dmitrii, so I'm very curious about the minimax lower bound you have shown in your previous slides. I forgot the number, but can you give us some intuition like this, the actual log term? What does it mean? Do you have some...
one sec. So the log n, or which term, or the fact that log of 1 over delta is additive? The second question is more interesting, by the way, but anyway. So which log do you mean? Log n? So S log n instead of S?
Yeah, I mean the log S, I guess. So you consider a class of linear recurrent linear recurrence of order S, so you pay an actual log term.
So yeah, one sec. Let me go. So first of all, slide where there are the rates, right? So let me show this, I guess, right?
Oh yeah, yeah.
Okay. Now, first of all, S log n, in fact, even log n over S, if we are being pedantic here, is the standard sparse recovery S log n over S. This is why. Among linear recurrences, linear recurrences just corresponds to shift-invariance of spaces. And in shift-invariance of spaces, there are those corresponding to sparse denoising. So if you consider recurrences with which the characteristic roots are degrees of unity, sorry, roots of unity of degree n, then this corresponds to just denoising, vanilla denoise, up to taking discrete Fourier transform with this bandwidth n. This corresponds to denoising a sparse vector in the Gaussian sequence model. And now, I mean, same explanation as in this case, why S log n over S? Well, because information theoretic complexity, right? I mean, you have n choose S possible positions of this, roots of unity, which, I mean, or in other words, you have n choose S positions for the support of this, Fourier support of the signal. And so you take the log of n choose S, and by stealing, you get, this, this is kind of the number of bits to encode the number of possible options, roughly. There is another related question, though. Okay, so if you look at papers by, Tank and Reicht and others, actually they have delta, 1 over delta inside this log. Which means that if you then decouple, you say the log of the product is the sum of logs, that means that it's not what I wrote here, it's that the second term is multiplied by S. Whereas the actual rate is not that. Now, this is actually a novel contribution. So what happened is that people in statistics kind of noticed that at some point. Okay, and then there was some work by Guillaume Lequet and others, like essentially using empirical processes, they managed to show in a very convoluted way that actually it's not, there is no S there. I think, I mean, it's Guillaume Lequet, also Nicolas Verzelian, like French people, strong French people did it, okay? Like maybe something like 2012, something like that. However, what happens is that there is another way of doing this. So with these filters, you can see where the stochastic terms comes from, and it comes from the L infinity norm. And so instead of doing lasso, essentially, okay, I never even described the statistical procedure, but let me show it to you. The statistical procedure is the following. Here it is. Estimator that we consider is this. So essentially, you do kind of least squares where you try to reproduce your data y by applying the filter phi.
Yeah.
But then instead of just L1 constraint that you would do with kind of this lasso ideology, which is still would not be lasso because this is y and not x here. Okay, this is y you try to reproduce. That's already different from lasso, but still uses only L1 norm. Okay, so it's kind of lasso on the support vector that is renormalized in a way to be of norm 1. But still, what happens that here we add L infinity constraint, where this would be of order S and this is of order 1. And because of adding L infinity constraint, what happens is that your set, this is still a tractable optimization problem because your feasible set is an intersection of L1 ball and L infinity. So you kind of cut out the corners from your L1 ball. But then you can also control the stochastic term because now L infinity norm is bounded. In fact, statisticians, statisticians, that would be, I guess, a better explanation of what I just said. But another explanation is the following, like why this L infinity constraint helps. In fact, extreme points of the L1 ball are one sparse vectors, right? So vertices of the L1 ball are vectors that are one sparse. Well, the problem is that if your prior information about the signal is that it's S sparse, that's not quite right? I mean, extreme points would better be S sparse as well. And this is actually where you lose. When you use L1 norm, this loses you the stochastic term, that S log 1 over delta instead of this. Because, I mean, noise kind of exists on the extreme points. This is the maximum. When you take it, it is an extreme. by Bauer's principle, meaning maximization principle of a convex function is attained on extreme points. However, if you instead consider this intersection, if you cut out the corners from L1 ball, now for this set, if you intersect the L1 norm of radius s and L infinity norm ball of radius 1, then the extreme points are actually S sparse vectors properly normalized. So S sparse vectors with identical non-zero components. And so they are the right ones. They model, in a way, this is kind of, this is actually the tight relaxation of, in some sense, this is the tight convex relaxation of the sparsity set, and not just L1 ball.
Okay.
That's kind of, yeah. Well,
Yeah,
thank you very much.
I'm also curious. So, so in practice, how you solve this optimization problem? You
yeah,
can
so
least square
yeah,
and then do the
yeah,
soft
good question.
thresholding.
We
plus
actually
some-
so without L infinity, we wrote a paper on that long ago in HTML. So we had specific methods. So essentially, you do first order algorithms where your like gradient, basically your first order oracle can be efficiently implemented using DFT, so using fast Fourier transform. So because of like Fourier here and there, like here everywhere is Fourier, right? And it's a Fourier, discrete Fourier transform matrix, and you can multiply by this matrix in like n log n. And you can exploit it to get really fast algorithms. Now, we never bothered at that time to do it with L infinity norm, and I would never write a paper about it. I'm totally done with it. But the idea is that it's not much different because this is an intersection of two simple sets, which is, because you intersect only two sets with different structure, you can do, no methods, something like alternating projection algorithms. People know how to do that. I mean, they maybe haven't bothered writing it for complex numbers, but you can do it. I mean, of course, what you can always do if you really want something quick, you can go to Mosaic, and this is a second-order convex program, second-order cone program, after just explicitly putting real and imaginary parts, and this will give you a slow algorithm, but you can code it very fast. But just if you really want something, problem adapted really quick, then it's something like mirror descent with the right potential for the set, which would still be entropy more or less, or like LP type potential.
Okay, so the computational cost is still in polynomial of both.
Very much polynomial. Not only polynomial, it's I mean, you get in the accuracy, you get typical scaling. I think the fastest we had in yesterday, we had the FGM method with this, where the gradient, first order oracle was implemented using FFT. So it was like it had scaling like often.
Okay. Yeah. Yeah. Thank you so much.
Thank you so much.
Yeah, I think, yeah. So
once again, I'm sorry for going over time. That's still a relatively new talk.
No, thank you so much for the interesting talk. Yeah.
Thank you.
So I hope to see you in person.
Yeah, and there was there was Roberto. Roberto was a very attentive listener whom I was staring at, and thank you for Roberto. He had to go, but Roberto Molinari, thank you so much.
Yeah.
Thank you.
Yeah. Okay. Bye,
Bye-bye.
Dmitrii. Thank you. Have a good day. Bye.
You too.